Can we reconcile the universe of the very big with the very small? That's the puzzle physicists are working on when it comes to quantum gravity.
Yeah.
And you sent over some really interesting stuff about this.
Right.
Especially about how general relativity and quantum mechanics clash.
It's a clash of titans, yeah.
They're both very successful in their own domains.
Exactly.
But it seems like at the most fundamental level, they speak different languages.
Like they're from different universes.
Like general relativity.
Yeah.
Einstein's masterpiece explains gravity as the curvature of space-time.
Caused by mass and energy.
It works beautifully for stars and planets.
And even the expansion of the universe.
But then we have quantum mechanics,
Right.
which governs the world of atoms and subatomic particles.
The bizarre world of atoms and subatomic particles.
And that's where the conflict comes in.
Exactly.
You know the video you shared, string theory versus loop quantum gravity? Wild Hunt for Quantum Gravity uses the example of a simple hydrogen atom. To illustrate this, quantum mechanics tells us that the electron exists in this fuzzy cloud of probability.
A superposition of multiple positions.
But general relativity says that this electron,
even though it's spread out,
should still warp space-time.
Yeah.
So where is space-time actually curving?
If the electron is in a sense everywhere and nowhere.
Good question.
It's like
trying to map a landscape.
Yes.
That's constantly shifting and shimmering.
Exactly.
So no wonder physicists are searching for a theory to bridge this gap.
Yeah, the stakes are high.
It's not just theoretical elegance.
Yes.
It's about understanding the nature of reality itself.
Exactly.
Take, for example, the singularity at the heart of a black hole.
General relativity predicts infinite density and curvature there.
That's a mathematical red flag.
Yeah.
It suggests the theory breaks down there.
Yeah, and we need a new framework to understand what's truly happening.
So it seems like general relativity might need an upgrade.
I think that's the growing consensus.
Even though it's been so successful.
Yeah, but think about the other three fundamental forces.
Okay.
The electromagnetic, weak, and strong forces. They all have quantum explanations.
But gravity's the odd one out.
Gravity is the rebel.
The rebel.
That refuses to follow the quantum rules.
Is that why physicists are trying to quantize gravity?
Yes.
To break it down into discrete chunks like the other forces?
Exactly.
So the quest for quantum gravity is essentially the search for a set of rules that describes gravity in terms of quanta.
Yeah.
These fundamental, indivisible units of energy and space-time.
Right, and there are two leading contenders in this race.
Loop quantum gravity.
It's string theory.
Okay, let's start with loop quantum gravity.
Okay.
It suggests that space-time itself isn't smooth and continuous, but is actually made up of these tiny, discrete chunks.
Like a pixelated screen?
Yeah, the video uses that analogy.
Yeah, pixelated screen.
So imagine the universe as this giant cosmic TV.
But instead of pixels.
It's woven from these fundamental units of space-time called quanta of volume.
The smallest possible Lego blocks of space.
And they're so tiny we can't even measure them yet.
Right.
So in this theory, space-time isn't a smooth sheet. It's more like a finely woven tapestry.
Precisely.
And the threads of this tapestry are interconnected loops and nodes forming what's known as a spin network.
Yes.
Each node represents a quanta of volume. And the way these loops connect and interact determines the curvature of space-time, which we experience as gravity.
Exactly.
So matter and energy warp this spin network, causing the loops and nodes to rearrange. And that's what we perceive as the force of gravity.
You got it.
It's so different from our idea of smooth, continuous space-time.
It is a radical departure.
But it offers some really intriguing possibilities.
Like what?
Like loop quantum gravity suggests there might be a limit to how much you can compress space.
A sort of quantum bounce.
Which could prevent singularities from forming.
That's the idea.
Wow, okay. My brain is definitely starting to bend.
I know.
But the video also mentions another player in this quantum gravity game. String theory.
String theory.
What's its take on all of this?
Well, while loop quantum gravity focuses on the fabric of space-time itself, string theory approaches the problem from the perspective of particles.
Okay.
The particles that inhabit that fabric.
Okay.
It proposes that everything in the universe, from the smallest particles to the forces that govern them, arise from the vibrations of these tiny one-dimensional strings.
So instead of point-like particles, we have these tiny vibrating strings.
Yeah.
Like the universe is a grand cosmic symphony.
I like that.
With different vibrations producing different notes, or in this case, the different particles we observe.
It's a beautiful analogy.
And what's fascinating is that string theory naturally gives rise to a particle that carries the force of gravity.
The graviton.
That's something that loop quantum gravity, at least in its current form, struggles to incorporate.
Yeah.
But I remember something about string theory requiring extra dimensions.
Yes.
Far more than the 3 spatial dimensions we experience.
String theory needs at least 9 spatial dimensions for the math to work.
9?
Yeah.
At least 9. But where are these extra dimensions?
That's the big mystery.
If they exist, why can't we see them?
String theorists believe these extra dimensions are curled up very small.
Okay.
Billions of times smaller than an atom.
So we can't see them.
And we can't detect them with our current technology.
So it's like a garden hose.
Yes.
From a distance, it looks one-dimensional, but up close, you see it has a second dimension curled up in a circle.
Exactly.
And string theory suggests something similar might be happening with space-time itself.
That's right.
So these extra dimensions are like tiny hidden pockets of reality.
Yes.
That is a mind-boggling concept.
That is mind-boggling.
But does this mean string theory has solved the quantum gravity puzzle?
Not quite.
Not quite.
String theory faces its own set of challenges.
Like what?
Well, for starters, there's no direct experimental evidence for these extra dimensions.
Okay.
Or for another key concept called supersymmetry.
And what is that?
Which predicts that every particle has a partner particle, a superpartner.
Uh-huh.
But so far, we haven't seen any signs of them.
So it seems like both loop quantum gravity and string theory have their strengths and weaknesses.
Right.
Loop quantum gravity reimagines space-time, but has trouble incorporating the other forces and particles.
Yeah.
And string theory offers a unified picture, but relies on unproven extra dimensions and supersymmetry.
Exactly.
Okay, so we've set the stage and met our contenders.
Oh, you have.
Let's dive deeper into the strengths and weaknesses of each theory and explore what evidence, if any, supports their claims.
Sounds good.
All right, let's dig into the specifics.
Okay.
What are loop quantum gravity's biggest strengths?
Well, as we discussed, it takes this bold step of quantizing space-time itself.
Yeah?
It suggests that the universe, at its most fundamental level, is built from these discrete, indivisible chunks. And this leads to some fascinating and potentially testable predictions.
Testable predictions. That's what we like to hear.
Right.
Tell me more.
For example, some physicists have proposed that in loop quantum gravity, the speed of light might not be absolutely constant.
Really?
As Einstein's theory of relativity suggests.
The speed of light being constant is like physics 101.
I know, it's a radical idea.
How could that even be possible?
Well, in loop quantum gravity, the structure of space-time itself could influence the propagation of light.
Okay.
Imagine those photons, particles of light traveling across vast cosmic distances. Loop quantum gravity suggests that photons with higher energy might travel slightly slower than those with lower energy.
So over billions of light years, even a tiny difference in speed could add up to a measurable delay.
Exactly.
How could we ever detect something like that?
Imagine a distant gamma ray burst a colossal explosion billions of years ago.
Okay.
If 2 photons with different energies were emitted from that event, they should arrive at Earth at slightly different times, according to loop quantum gravity.
So we're talking about incredibly precise measurements of photons arriving from the depths of the cosmos.
Yes. Very precise measurements.
Has this time delay been observed?
Not yet. It could be that our instruments aren't sensitive enough to detect these subtle differences.
Okay.
Or it could mean that this particular prediction of loop quantum gravity needs refining.
So it's possible?
But the possibility of testing such a fundamental aspect of physics is what makes this theory so exciting.
It's a reminder that even the most established ideas in science are open to revision.
Absolutely.
Okay, so even if that specific prediction doesn't pan out, the idea of quantized spacetime is still a major departure from our everyday experience.
It is a radical departure.
But loop quantum gravity faces another challenge.
What's that?
It doesn't easily incorporate the other forces and particles described by the standard model of particle physics.
Yeah, that's right.
It's primarily focused on gravity.
It is.
So it's a theory of quantum gravity, but not necessarily a theory of everything.
Right. It doesn't yet offer a unified picture of all the fundamental forces.
Okay, and this is where string theory comes in with a different approach.
Yes, string theory.
Okay, back to string theory then.
Right.
It's known for its mathematical elegance.
It is.
But you mentioned it faces some challenges, too.
Yes, string theory is incredibly appealing in its attempt to explain everything in the universe.
Everything.
All the forces, all the particles as arising from the vibrations of these tiny one-dimensional strings.
It's the ultimate reductionist dream.
It is.
Finding that one fundamental ingredient and explaining everything else in terms of it.
Exactly.
And it manages to incorporate gravity naturally, right?
Precisely. One of the most attractive features of string theory is that it naturally gives rise to a particle that carries the force of gravity.
To graviton.
The graviton.
This is something loop quantum gravity, at least in its current form, struggles to do.
Yes.
So string theory gives us a quantized description of gravity.
Yeah.
And potentially unifies it with the other forces.
It has a lot going for it.
It sounds like it, but what about those extra dimensions?
Yes.
That's a pretty big pill to swallow.
Yes, the extra dimensions are a key feature of string theory.
Okay.
And they're both fascinating and problematic.
Yeah.
As we discussed earlier, string theory requires at least 9 spatial dimensions for the math to work consistently.
9.
These extra dimensions are thought to be curled up incredibly small, billions of times smaller than an atom.
Okay.
This is why we don't experience them directly.
So if we can't see them,
Right.
or even detect them with our most powerful instruments,
Yeah.
how could we ever prove they exist?
That's one of the biggest challenges facing string theory.
Okay.
Some physicists believe that if these extra dimensions exist, they might manifest themselves in subtle ways, perhaps through their influence on the behavior of particles at very high energies.
Okay.
Others are looking for signatures of these extra dimensions in cosmological observations, such as the cosmic microwave background radiation.
So it's a waiting game, hoping to find some subtle hint of these extra dimensions in our experiments or observations.
Exactly.
But what about supersymmetry? Didn't you mention that was another key prediction of string theory?
You're right. Supersymmetry is crucial in many string theory models.
Mm-hmm.
It predicts that every known particle has a superpartner particle, a sort of hidden twin.
Okay.
And these superpartners, if they exist, could solve some long-standing mysteries in particle physics.
So supersymmetry sounds promising.
It does.
Have we found any of these superpartner particles?
Despite extensive searches at particle accelerators like the Large Hadron Collider, no signs of superpartners have been found. And this has led some physicists to question whether supersymmetry, as it's currently understood, is truly a feature of nature.
So once again, we have a theory that's elegant and compelling mathematically.
Yeah.
But lacks direct experimental support.
That's right.
It seems like both loop quantum gravity and string theory are facing similar challenges.
That's a keen observation. They're both works in progress, pushing the boundaries of our understanding.
Yeah.
But also facing significant hurdles.
Uh-huh.
And this brings up another important point.
What's that?
Both of these theories are incredibly complex, requiring sophisticated mathematics to describe them.
So even if we had a perfect theory of quantum gravity understanding and interpreting, it might be beyond our current capabilities.
It's a real possibility. The math involved in these theories is so advanced that even physicists who specialize in them are still grappling with its full implications.
Wow.
And this complexity also makes it difficult to come up with testable predictions.
So we're searching for a theory that might be so profound and so complex that we might not even recognize it if we found it.
It's a humbling thought.
It is, but that's the nature of scientific exploration, right?
It is.
We're constantly pushing the boundaries of knowledge, venturing into uncharted territories.
Exactly.
And sometimes the most difficult questions are the ones that lead to the most profound discoveries.
That's often the case.
Okay, so we've explored the strengths and weaknesses of both loop quantum gravity and string theory.
We have.
They both offer intriguing glimpses into the nature of quantum gravity. But they also raise more questions than they answer.
Indeed. And it's important to remember that these are just two of the leading contenders in the quest for quantum gravity.
Right.
There are other approaches being explored as well, each with its own set of assumptions and predictions.
So the search continues.
It does.
But before we get too lost in the theoretical weeds, let's step back and consider the bigger picture. So why does all of this matter? I mean, these theories are fascinating.
They are.
But what's the real-world relevance?
That's a great question.
Yeah.
It's the question that drives every scientist, I think.
Right.
These theories aren't just abstract mathematical exercises.
Yeah.
They could completely revolutionize our understanding of the universe.
At the most fundamental level.
The most fundamental level.
You're saying there's more to this than equations on a chalkboard.
Absolutely.
Yeah.
Imagine the possibilities if we could really understand quantum gravity.
Like what?
Manipulating gravity.
Okay.
Understanding what happens inside black holes. Maybe even unraveling the mysteries of the very first moments of the universe.
Right now, it's like we're looking at the universe through a foggy window.
Yeah, a very foggy window.
And quantum gravity could wipe that window clean.
It could give us a crystal clear view.
And who knows what could come out of that?
Yeah.
What technological advancements?
New energy sources.
Okay.
Revolutionary propulsion systems.
Uh-huh.
Ways to manipulate space and time.
That's like science fiction.
It does, but so did many scientific breakthroughs before they became reality.
Right. Like airplanes.
Exactly.
Okay. I'm starting to see why this is such a big deal.
Yeah.
Even if we're generations away from any practical applications,
Yeah.
the pursuit of knowledge itself is worthwhile.
I agree completely.
It's about pushing the boundaries of human understanding.
Exactly.
And expanding our horizons.
And you know, the search for quantum gravity is forcing us to develop new tools.
New tools, like what?
New mathematical tools, new experimental techniques, new ways of thinking about the universe.
Makes you wonder what Einstein would have thought about all of this.
I know.
He dedicated the latter part of his life to a unified theory.
He did.
And we're still grappling with the same fundamental questions.
It really shows how deep and complex these problems are.
It does.
But it's also inspiring to think that somewhere out there, the next Einstein might be working on the breakthrough. That changes everything.
I wish we could fast forward 100 years and see where we end up.
I know, me too.
But before we wrap up, I want to go back to that pixelated universe idea.
Okay.
You said space-time might be made of these tiny, discrete chunks.
Yeah, like the pixels on a screen.
What happens at the edges of those chunks?
That's a question that keeps physicists up at night.
What lies beyond the limits of what we can perceive?
If space-time is fundamentally granular, does that mean there's a limit to how finely we can divide reality?
And if so, what's beyond that limit?
Is there some ultimate resolution to the universe, like the pixels on a screen?
And what's beyond those pixels?
Is there some realm of existence so small that it's beyond our comprehension?
It's amazing.
It is.
Science isn't just about finding answers.
No.
It's also about asking the right questions.
Exactly.
And the quest for quantum gravity is pushing us to confront the limits of our knowledge.
It is.
And to imagine new possibility.
Possibilities that might seem outlandish today.
Like could become the breakthroughs of tomorrow.
Exactly.
It's a reminder that even when we're faced with these huge challenges, the human spirit of curiosity and exploration will always drive us forward.
It will.
We may not have all the answers yet.
No.
But the search itself is incredible.
I agree. The quest for knowledge is an endless adventure.
It is.
And we're lucky to be a part of it.
It's exciting to think.
It is.
About what wonders might await us as we keep probing these mysteries of the universe.
I can't wait to see what we discover next.